Hello, everyone. Thank you for joining us today for this PIC Magazine webinar, hosted by Expo, Hewlett-Packard Enterprise, HPE, and MPI Corporation. My name is Mark Andrews, and I will be your moderator. I am technical editor of PIC Magazine, Silicon Semiconductor, and Power Electronics World within Angel Business Communications. Photonic designers, developers, and manufacturers recognize that realizing the dream of photonic integrated circuits, PICs, as mainstream components has been hampered by the lack of integrated test, assembly, and packaging systems. Simply put, TAP has held us back. Optical testing at the wafer level is currently a major manufacturing bottleneck due to the tighter tolerances required when compared to electrical testing. The methods used most frequently today in optical testing and component assembly account for 80% of final product cost. 80%. Expo, Hewlett-Packard Enterprise, and MPI Corporation have combined forces to address the challenges of optical component testing through the development of advanced interoperable measurement techniques. This three-way collaboration has resulted in a testing solution that makes wafer testing faster, scalable, and more reliable, ultimately improving speed to market for manufacturers. Faster, more accurate testing processes help ensure greater reliability, which can lead to a higher quality product overall. This sets the stage for PICs to play a vital role in next generation networks, including 5G deployments and high-speed data centers. Today, we will hear from three speakers representing each member of the collaborative development team. Lawrence Van de Vek is Expo's subject matter expert for passive and active device component testing. He focuses on the unique testing requirements of PIC technologies. Ashkan Saidi is a senior research scientist at Hewlett-Packard Enterprise. Ashkan's most recent work is focused on developing high bandwidth, high efficiency optical interconnects for exascale and high performance computing applications. Representing MPI Corporation is Sebastian Geisman, who is presently responsible for probe systems product marketing thanks to his expertise in silicon photonics testing. All of our experts have addressed the topic from the perspective of their companies through pre-recorded presentations that detail how the new testing solution was developed, while also describing the opportunities it presents for PIC manufacturers. We will return to take live questions from the audience once the third presentation concludes. Whenever possible, our presenters will answer questions live. However, some questions require complex answers, and in these cases, presenters frequently speak to the subject briefly, indicating that detailed technical replies will be sent once the webinar concludes. Expo, HPE, and MPI hope to answer all questions live, but when this is not possible, please look for email replies that are typically sent as soon as possible, which is usually within 24 hours. Those registered for the webinar will also receive an email from Angel Business Communications indicating when the full recording is available for replay. So, without further ado, please join me in welcoming the presentations of Lawrence Van de Vek, Ashkan Saidi, and Sebastian Geisman.
Thank you, Mark, for the introduction. My name is Ashkan from Hewlett-Packard Enterprise. I work at Labs, and I will tell you a little bit about our silicon photonics efforts and the challenges therein that we will address today in this webinar. So we at HPE have recently transformed. We split the company 5 years ago, and then we're kind of pivoting into this solution-based company where we realize that everything is connected, that we must have intelligence everywhere. Here you see some what we claim to be intelligent tractors, if you will, addressing the agriculture world. And also then when you generate a lot of data, you have to be able to analyze it and infer actionable results from it, such as improving someone's health or improving someone's customer experience or making money. So this is a definition of what the company is and what we're doing, where eventually, actually today even, everything computes. All the devices have some sort of intelligence integrated into them. A slight overview of the company. We are the classical hardware and infrastructure company moving into the as a service company where, we do a lot of work in the servers and are world leaders in that and associated storage with it. We recently acquired some leading companies where we've significantly improved our lead in the HPC market, the high performance computing market world, and where we're also remaining to play in the hyperconverged infrastructure for the typical data center. We have also a great deal of experience and product portfolio in the enterprise LAN and switching world through Aruba. And here you can see some of the publications where we have been able to attain records and get some honorable mentions there. As a portfolio, or as a profit portfolio, we are around 7 billion a quarter. Here's a split amongst the world of what we do. And I just mentioned, the intelligent edge, compute, HPC, et cetera. So you can see that in storage and in compute are areas where we significantly lead and have a huge market capture, and also beginning to dominate more and more in the HPC space as well. Now, zooming into the photonics, to be able to enable competitive market products and to really break the bottleneck that we all know about for data movement, we've invested a lot of work on some of the foundational IP and system leadership, where we developed 2 parallel optical paths. One is VCSEL-based for the traditional rack level multi-mode fiber solution. The other one is what we're referring to as Silicon Photonics for the longer distances, single mode solution. And we imagine a world where everything kind of exists together and are used judiciously where it makes sense, for the data rate makes sense, for the power, the cost, all of that makes sense. And here we're showing you some of the generational data rates for the on-chip optics, referred to as Silicon Photonics due to the co-packaged form factor that I will be addressing a little bit today. So part of the co-packaged experience, being able to build a co-packaged solution, requires that we treat optical components much like we do electronic components. And to compare the two design experiences is very different. The electronic chip design world, I compare it to a smart car driving 100 miles an hour down the freeway, built on 50, maybe 60 years of IC development, right? Since the mid-50s, when the initial ICs were built, there's a plethora of tools, methodologies, ways of modeling and abstracting it, thousands of pages of standards, and many, many foundries who have developed the process from which you can build 16 nanometer, 12 nanometer, 7, 5, and even 3 nanometer devices to lead the mobile world, the HPC world, et cetera. Comparing that to the photonic chip design world, it's, we used to be that ape on the far end here, and we have slowly begun walking. And I think we're in the middle form factor here, where we just learn how to sharpen some tools, but soon we'll be the lady in front with the spear and the person at the very end with the briefcase, right? But today, there's limited foundry availability. Maybe competitively across the world, there's less than 10. The electronics tools have been forced and mutated and massaged to do photonics. The testing is completely essentially manual. If you're lucky, you'll get some automated testing work, which is some of the subjects we'll talk about here today, between the equipment that Lawrence will talk about and some of the testing equipment that Sebastian will talk about. And there's still a lot of challenges that need to be overcome to take that data and do something with it, build models, build abstractions. But luckily, I feel like since the electronic chip design was carving the path and have set the expectations, and there's millions of mixed signal designers out there, we know what it's supposed to look like. It's an open note test. We can see the end goal and the standards to strive to, so it lets us gain that ground very quickly in the photonic chip design world. At HPE, we not only build systems, we also work to enable the environment. And here I'm calling it the ecosystem, but it's really the market enablement, right? So it's not enough just to give someone one part of the solution. They have to be able to have an end-to-end experience on designing something, getting it made, getting it assembled, tested, and then in their hands at the end of the day. So the PDK, the product development kit that we're working on, is based on a foundry process against which we've qualified our devices. And we would license that PDK, for example, to customers, even our own business units. And they would go through design automation tools to build a design database give it to the foundry would fabricate it, send it to an assembly partner, who would then send it to a contract manufacturer for board level, and out would come a product. And into that assembly partner is where the key green box in the lower right here plays a role, where you see some of the equipment from Expo and MPI plugging in at the foundry into the assembly partner level, because the foundry needs to be able to deliver known good wafers, known good dies, for example, if you choose, or at least meet some process spec. Currently, this is done electrically by looking at, for example, contact resistance or sheet resistance, etc. You have to have that analogous testing equipment and spec for the photonic world, such as insertion loss for your grading, for example, or the optical bandwidth of your grading, whatever the customer desires. Currently, most foundries cannot do that. They give you your solution, they give you your wafers, and they just say, okay, well, best of luck, and I hope it works. There's no way to guarantee that across the wafer. Similarly with the assembly partner, as the pluggable silicon photonics starts to ramp up, some assembly houses are learning how to do semi-automated testing, but it's still not anywhere near where it needs to be to hit mass volume. And we'll address some of those challenges today on what it needs to look like. And a quick word on kind of the market alignment of the PDK, as I said, based on a foundry process. There's a library. That library entails some components. Here you can see some abstracted black boxes with some pads and waveguides and stuff for some of the devices, showing you bands, grading couplers, modulators, etc., where then you would do a typical chip layout. For example, here's a 56 gig PAM4 MZI-based link. Here we have a ring modulator link, and here are the devices that are used to build that link. But before you can do that, you have to have many, many gigabytes of test data from which you can build these models, so that you know when you put something down in silicon, you know what it's going to look like before you get silicon out. And the way we went about doing that was we would do what we call the design of experiments test chip flow, right? So where we would just take one single device, various geometry in every way that we could think of, measure it, map the geometry changes to the observable changes using a grading coupler, which you'll see a video of later, is, for example, the insertion loss, the optical bandwidth. You can play with the etch depth, you can play with the duty cycle, etc. And you understand the process bias and the design dependence on those observables. So you fabricate that, you design that in the DOE, you send it to your foundry who builds it, then you have to do automated wafer level testing. And that wafer level tester must meet certain criteria like speed and accuracy and repeatability, which we'll talk about. Then you take all that data, ingest that, and come up with your design rule deck and supplement your PDK models. And in this way, you're able to actually build something that's manufacturable and useful in the commercial space. Here's an example. So on one of the chips that we did, there are roughly 2,500 rings. They're the same device, just permutated in their radius, gaps, waveguide width, everything. But they're really mapped to the observables of free spectral range, the Q, the extinction ratio, the insertion loss, etc. So here you can see I've abstracted some of the numbers away. So thank you for bearing with me on that. But you can see as we vary these 5 different parameters, we see different behavior. The red line represents the resonance wavelength, right? And you vary the radius, and those get smaller and larger, et cetera. So understanding that. But in order to be able to infer this data and make some model updates, you have to have a testing solution that is fast, reliable, accurate, because if you see the wavelength and resonance changing by 0.1 nanometers, for example, is that because the tester and the laser are inaccurate, or is it due to your device, right? And to give you a sense of scale here, the wavelength and resonance here is measured with 2 picometer at resolution, maybe even 1 picometer resolution. So it's very high fidelity, very repeatable, very accurate. Like if you measure the same thing 100 times, do you get the same result, etc. So, and the comment about it being fast, I mean, 2,500 rings on one reticle, there's 80 reticles on a wafer, there's 25 wafers on a lot. So you don't want to be spending 6 months testing just to be able to build your data. So it needs to be very fast and reliable. And so I hope this captures the specific challenge and application that at least we have in mind, and where the solution that we propose today will be extremely well competitive. So in conclusion, I hope that I've been able to convince you on why these few attributes are important for what we're doing for enabling the PDK in the ecosystem, and to drive Silicon Photonics into the mass market by enabling a design experience that matches the IC world. And so I put some numbers behind it, right? So it needs to be fast, less than 5 seconds per device, ideally 2 to 3 seconds. It needs to be accurate. You need to have ideally 1 nanometer or better precision of your movement. You need to have repeatable measurements. So less than 500ths of a dV gauge repeatability, so that if you align, move, come back to it, you get the same result. And you need to be able to add tests. Today you're testing gratings, tomorrow it's this, tomorrow it's that. You want to add electronic control, thermal, polarization, etc. So you need to be able to add these tests in a somewhat of a modular fashion. In an ideal world, it needs to be fully automated so that you can basically load the wafer, load the test program, do some alignment and setup, press play, and just walk away and know that you get your either pass or fail, essentially. And you have to have a hotline, because if something breaks in the hardware and the software, you have to know who to call to get it fixed. And this is the only way that this can actually be supported in the foundry and in the testing assembly floor, such that because the technicians themselves cannot be fixing it, right? So I hope I set the stage today. I hope you're intrigued. The speakers after me will address how we're solving these challenges today, starting with Lawrence right after me. Thank you.
Welcome everyone to the test and measurement part of this webinar, and thank you, Ashkan, for outlining the challenges that the PIC industry faces as a whole. In this presentation, I would like to provide an outline on who EXFO is, the collaboration objectives between the 3 companies, and the solutions that we provide. So who is EXFO? EXFO is a well-established company and has been around for over 35 years, with its core roots not limited to just fiber optic testing. It provides test solutions on component level, subcomponent level, system level, and network level, which includes active monitoring and real-time analysis and fault prediction. This presentation will be focused on testing of active and passive components used in a wide variety of applications. Since actual testing is just one aspect of characterizing photonic integrated circuits, the decision was made to collaborate with HPE and MPI. So the main objective of this initiative was to provide solutions rather than just test instrumentation. This enables the possibility to provide turnkey solutions based on the customer's needs and not too limited what just EXFO has to offer. This in turn, this collaboration prevents situations where any issue turns into a finger-pointing match. And as Ashkan highlighted in his presentation, full ecosystem support can be provided from design into full-scale mass manufacturing. This photo sums it all up. Wafer disk technology provided by Hewlett-Packard Enterprises, handling of the wafer disks and alignment of the probes by MPI, and the actual testing by EXFO. This photo sums it all up. Wafer disk technology provided by Hewlett-Packard Enterprises, handling of the wafer disks and alignment of the probes by MPI, and actual testing by EXFO. In this example, we see a CTP10 passive optical component tester with 2 tunable laser sources and a PDL controller for testing passive PIC components. The top screen on the right shows the measurements taken by the CTP10, and the screen right below it shows the alignment and the control of the wafer disk controlled by MPI's TS3000, on which Sebastian Giesman of MPI will be providing further details in his presentation. So what are the typical objectives when testing photonic integrated circuits? As always, time is money, which means objective number 1 is keeping testing time as short as possible. With the ever higher speed performances of new PIC designs, it's critically important to select instrumentation that's capable of measuring faster than the actual response time of the PIC itself. Having to run tests at 2 nanometers per second, while the hardware is capable of scanning at 100 nanometers per second, for instance, just to be able to get reliable results will only increase the measurement time. And of course, this ties in with the accuracy of the system, which should leave absolutely no guesswork. Since the characteristics of a PIC can be very wavelength dependent, one needs to know at any given time what the exact wavelength or loss of power is. Repeatability is important since the measurement should only be done once. Having to run scans multiple times to come to accurate results will only add to the total measurement time, which is obviously not something that, that one wants. Being able to add functions and features over time to an investment already made makes obviously always the best sense. Coming to the actual portfolio of test instrumentation that EXFO offers for PIC testing applications, is what is shown here. The combination of the T100S HP family of SWEP-type tunable laser sources combined with either a CTP10 or CT440 can be used for passive component testing, whereas the fast scanning OSA20 comes in for active component testing. These products allow for testing of pretty much any active or passive device or even hybrid devices, not too limited as what is listed here on the left. This is a typical PIC wafer test setup. The example here shows a CT440 with 2 tunable laser sources that are connected up with 2 optical probes onto the PIC itself, controlled by an MPI probe shown at the bottom right. Depending on what the device under test is, one can use, for instance, a current source to electrically control the PIC and measure the electrical current conducted by the PIC. Having the entire system controlled by one PC allows one to correlate the optical performance of the PIC with the electrical performance and actually determine the quality of the device under test. An example of an optical electrical PIC is shown here, a popular product like the a Mach-Zehnder modulator. So as these graphs show here, applying different voltages to the modulator results in a change of the optical spectrum response, which is here measured with a CT440 and a T100S HP. And these tests were run by CIA Leti, which gave us the courtesy to share this data. Another example here by CIA Leti is testing of a 4-channel PIC transceiver, again using a CTP10 with a tunable laser source, or a CT440 for that matter could be used as well. So when looking at the actual instrumentation used for PIC testing, EXFO offers 6 different models of the SWEP-type tunable laser source family, the T100S HP, covering 1240 to 1680 nanometers. The uniqueness of these lasers are the extremely high dynamic range of 100 dB or more, which is pretty much the net dynamic range that one can use for testing PIC. Coupled with a sweeping resolution of 1 picometer intervals at a speed of up to 100 nanometers per second. The CT440 passive optical component tester is the pre-successor of the CTP10, which I will highlight in the next couple of slides. But they both offer the uniqueness of optical triggering versus electrical triggering using an interferometric system. And this system allows for wavelength monitoring with an accuracy of 5 picometer or better, while the system is in action. The CT440 is available with various port configurations and with PDI options as needed. So once the system is wired up as shown on the right, all there's left to do is pressing the start button on the computer, and within a couple of seconds the spectral response curve or curves will be shown, as is simulated here. The interferometric nature of the system provides an extra feature, which is wavelength measurements of an active source or signal, highlighted at the bottom here. I can further elaborate on this during the Q&A session at the end of this presentation, or you can always reach out via an email where I can provide further details on this. The CTP10 is the CT440's big brother. It was brought to market about 3 years ago now, and very well appreciated. And so it can be seen as a CT440, but with more port, tighter specs, an integrated operating system, and a lot of additional features. And as this picture shows, the CTP10 is equipped with 2 high-speed electrical output ports, shown here on the right, which can be assigned to any detector installed in the CTP10. So it converts any optical signal into an electrical signal, and that signal can be used for a probe to PIC optimization by the MPI handler in this example here. But nonetheless, you're not limited to any brand or any type of wafer probe handler. And of course, those electrical signals can be used for other purposes as well. The CTP10 GUI, or graphical user interface, is extremely user-friendly and intuitive. As shown here, there is a dedicated screen for each step of the process, again, making it very simple to use. From defining the hardware used in the test setup, the optical wiring of the system, the PIC under test itself, measurement itself, and then the results and the auto analysis. So as these 4 screens show, it is one turnkey automated test solution from setup to results. So this slide makes us go full circle back to the turnkey one integrated test solution with the objective of keeping testing time to a bare minimum. The bottom right shows the steps the system undertakes testing a typical wafer disk. So the first step is to auto-align the probes, the in and outputs on the PIC itself, which depending on the device can be as short as 0.5 seconds, so half a second in this typical single port use case. The PIC tested here is an O-band device, part of a wafer disk designed and provided by Ashkan of Hewlett Packard Enterprises. Okay, so after the alignment, the CTP10 is triggered to make an auto measurement. This is on two devices, as you can see here on the right, the scanning time. So this is the first device, the second device. After that, we zoom in at the area of interest. So after completion of the measurement, the CTP10 will automatically provide the analysis data on the PIC measured, bringing the total measurement time in, again, in this use case of a single device, just to 5.5 seconds. Again, extremely fast. A note to make here at the bottom right, where it says, the wavelength accuracy is a maximum of plus minus 5 picometers, on which we provide options to bring this down into the sub-picometer accuracy range, typically required for a ring resonator testing. So the interferometric nature of the CTP10 provides a well-appreciated feature, which is shown here, which is fault location within the PIC itself at the micrometer resolution. I won't be going into the details here, but reach out after this presentation during the Q&A session with more questions on this topic, or send me an email which allows me to provide further info on this. Active PIC testing requires different instrumentation, and this is where the fast OSA 20 comes in. The speed comparison shown on the top left confirms that depending on the sensitivity level set, the OSA 20 is an average about 10 to 15 times faster than any other grading-based OSA on the market at the moment, without any compromises. And as mentioned at the beginning of this webinar, time is money, not just for the CTP10 or the CT440, but of course the OSA 20 as well. So time is money, which makes this as a key feature of the OSA 20. The OSA 20 is typically used for measuring PIC laser diodes on SMSR, so side mode suppression ratio, on power and wavelength, which is where the 20 picometer fixed optical resolution comes in very handy. And this is what is shown on the bottom right, comparing it to other grading-based OSAs that have an adjustable slit, creating these shoulders, as shown here and in blue on the bottom right. The OSA 20, as mentioned, has a fixed optical resolution, which eliminates that problem on the OSA 20. So this concludes my part of the presentation, which showcased a typical example of what EXFO can do on providing test solutions with an open collaboration with HPE and MPI. So for now, I will be handing it over to Sebastian Giesman of MPI, who will be outlining the utilization of the wafer probe handler. Thanks again, and feel free to reach out during the Q&A session.
Thank you very much, Lawrence. I will now proceed with my part of the presentation, which concentrates on integration of the Silicon Photonics test solutions on a wafer probe station. My name is Sebastian Giesman, and I work for the MPI Corporation as a product marketing manager. Just, I want to do a short company introduction. The company MPI was founded in 1995 and has now over 1,500 employees worldwide. There are 4 divisions within MPI. First, there is the probe card division, which is providing different kind of probe card technologies for production probe systems. Then we have our thermal test systems division, which is delivering thermal streams for testing under temperature. For the probe stations, we have our photonics automation division, which is the worldwide market leader for LED probe stations, but also provides solutions for sorter and automatic optical inspection. The division I work for is the Advanced Semiconductor Test Division. We are concentrating on different applications for high-frequency device modeling and wafer-level reliability, but also high power, and the topic I cover in this presentation, Silicon Photonics. To test Silicon Photonics, we can do this on different kinds of probe stations. There are certainly manual probe stations available, but the target is to do an automated test in an automated probe system. So we see here a variety of probe systems. Start on the left side, which is a 200 millimeter semi-automatic probe station. So this probe station can test a wafer, which is manually loaded by the operator, and then can test the wafer in a fully automated manner. In the center here, we see the same version in a 300 millimeter wafer. And on the right side here, we have the option to add a loader module to a 300 millimeter probe station and test fully automated wafer after a wafer. So all the loading is also done automatically with a robot, and we can test over a day or overnight as well, many wafers. So now these probe stations, we need to optimize for the Silicon Photonics test requirements. So based on our standard probe stations, we did the modification to certain parts of the probe station. So first, we provide a very high stability probe plating, because on the probe plating are the alignment positioners located, and they need a very stable environment to minimize the vibration influence. Then we need to integrate the additional control equipment for these alignment positioners. And this can be integrated in a separate rack to the probe station, but this will consume additional floor space. So therefore, we integrated this here right in the corner of our probe station above the thermal chuck chiller to not consume any additional floor space. To do the actual measurement, we are providing an instrument shelf, which is put here in the back of the probe station. And here we place all the optical equipment like laser or power meters and the electrical instruments like a VNA or a parameter analyzer. This is good to have a seamless measurement integration very close to the device under test. The optical fiber setup, we have different configurations. there is a one-sided setup possible. What we can see here in this picture, this is for light emitting or light detecting devices. That means we have an optical probe on one side and we have an electrical probe on the other side. So the optical probe could be a single fiber or fiber array, and the electrical probe, in this case here, it's an RF probe, but could be also a DC setup. The other possibility is to have a double-sided optical fiber setup. This is for components with an optical input and optical output. And in this case here, both fibers are aligned for the sender and the receiver. Additionally, we can have also electrical probes in here. For instance, an RF probe or a DC probe coming in from the north or the south side of the probe station. For the alignment option, we have different possibilities. The first one you see here in this picture. In this case, we are using 2 hexapods to do alignment for multi-channel fiber arrays. The hexapods are necessary because we need to take care of the rotational misalignment of the fiber array. So in this case, we use an XYZ linear coarse positioning to position the fiber over the input and output, and then align the array to the inputs and outputs of the device. So therefore, we have this rotational alignment. And to do the final precise alignment, we are using an integrated 100 micrometer nanopositioner. This nanopositioner is a piezo-based positioner, and it's moving in X, Y, and Z. So it's a linear positioning. So, and the reason why we have this additional positioner with this very small movement range is that it provides a very fast and very accurate alignment. Alternatively to the hexapods, we can have a linear coarse positioner. In this picture here, we see the 2 coarse positioners, which are a 13 millimeter XYZ positioner stage. So this setup is mainly used for single fibers. Could be also a one-sided or double-sided setup where the fiber is roughly positioned over the device under test input or output. And then we use the same integrated nanopositioner with its 100 micrometer XYZ movement range to do the fine alignment. So both cases are using the same final alignment technology. So this functionality needs to be integrated into the probe station environment. So therefore, we need to look at 2 different things. So first is the integration into the software. The software for a probe station typically takes care of all the positioning and alignment of the stage and the microscope to their probes. So here we have the additional stages for the optical fiber. So all of the requirements and functionality for this optical fiber positioning is integrated into the software. So we have different controls here, which are taking care of all the alignment and also the angle alignment for the hexapod. Integrated into our hardware control panel, which takes care of the microscope and chuck positioning. For standard probe systems, we have the hexapod functionality also integrated in here to do a coarse alignment of the fiber to the device under test. The advantage here is that no additional joystick is needed to do any kind of positioning with this optical alignment positioners. Besides the standard functionality, we have some special requirements for the fiber alignment. So for this fiber alignment, we are providing wizards within our software, which makes it very easy and intuitive for a user to go through the setup before he can start to take measurements. So the important thing here is that we don't require an additional third-party software, which takes over an additional screen. Everything is nicely integrated just in one software environment. So here we see a typical setup of the probe station. We have the 300 millimeter probe station with 2 hexapod positioners Then we have the measurement set up here in the back. The two monitors are used here for the probe station control, which is the lower monitor. And on the upper monitor, we show the measurement setup and measurement results. Now I want to explain how the optical alignment is done. You see here the same picture I have shown before with the two optical positioners where a fiber is connected to connect to the device. So to one fiber, we connect an X-FO laser. This is feeding a laser signal into the device. And on the other side, the light is captured with another fiber and connected to the CDP10 X-FO power meter. So now this optical information, which is captured from the power meter, is converted into an analog output value and feed into our positioning control system. And with this information, the positioning control system is able to align the left stage and the right stage to an optimum coupling position to do a measurement afterwards. The alignment is done in different steps. So first, we need to find first light. This first light finding is a manual action. So we do this only at the first die, where the fibers are roughly aligned over the optical input and output. After that, we can give complete control to our automated functionality. In this case here, we do first an area scan, and we see how the area scan is done, that we use a spiral scan where we start in the center, and in spiral we go to the outside of the 100 by 100 micrometer movement range and look for the highest optical feedback value. So after this scan is done, we position the fiber at this maximum value. To fine-tune the whole coupling, we use a gradient search, which is followed after the area scan. So this gradient search can do a parallel optimization of the global maximum and positioning both fibers for an optimum light coupling to have good measurement results. So because all of these different components need to be integrated into a test executive, which is managing the whole test procedure, we are providing free Python-based sample scripts. So these sample scripts, they include everything what is required to do an automated test flow. So for the probe station, we're providing commands which take care of everything what needs to be done after the wafer is placed on the chuck. So this can be the automatic wafer alignment, the automated home positioning under the device, under the first die. Then we do an automated fiber alignment. This is done all automatically through these Python-based scripts. But we can also initiate the actual measurement where we connect to the optical test equipment. So all of these scripts can be integrated in a customer test executive and can be customized according to the requirements. Here we see a typical measurement setup. Again, we have this only an optical setup here where we have a fiber input and fiber output, which are connected to a laser source and to the CDP10 here to measure the optical feedback. In this case here, we have a combination of optical and electrical measurement. On the left side here, we see a probe with a fiber array. So this is on one side, and on the other side, we have a probe card. So this probe card is a U-shaped probe card here, which is connecting the device electrically. A workflow will look like this. So the first is the manual action of finding first light. After that, we do an automated area scan, and the result of the automated area scan is shown in this graph. We see here on the two axes the 100 micrometer movement range in X and in Y. And on the Z axis, we see the power reading. So this is a nice graph where we have no feedback in the outer area. And then in the center area, about the maximum, we have the different reading. So after that, the fiber is positioned at this maximum reading here. So this scan is followed by the gradient search again, which is an optimization of both fiber positions. So after that, we are actually able to take a measurement. Typical measurement would be here an IL or PDL measurement. We see here a screenshot of an example. So after that, we stepping to the next die, and to reposition the fiber, we do another gradient search before we are taking another measurement. So talking about timing here, this is what we have done with the HPE wafer, where the alignment took about half a second when we did the gradient search for repositioning the fiber, and then the actual measurement was done in less than 5 seconds. The stepping next die is always depend on the wafer size, and also depend if I just do a little subside step or a large step next die. In this video here, we show the actual stepping of the 2 fibers on the HPE wafer. I will start the video now, and I see here on the left side is the input fiber, and on the right side is the output fiber. Both fibers are aligned and taking measurement. Now we see the 2 fibers moving to the next sub-die within the die, so there's no chuck movement done. And after repositioning, it's moving to the next die. So now we saw the chuck moving to the next die, and the fibers are positioning, and then the next die is measured again. And then this can go on and on after the whole wafer has been tested. Another important point is the requirement to test at temperature. We are providing different thermal chucks to test the temperature. We basically start with a standard chuck, which goes from 30 degrees C up to 200 degrees C. So after that, this chuck can be also upgraded to up to 300 degrees C or as low as minus 60 degrees C. For the Silicon Photonics test requirements, we can provide an environment which goes as low as minus 40 degrees C or up to 200 degrees C. So this chuck can be chosen right in the beginning as well. To do other types of application, we can certainly equip the system from minus 60 up to 300 degrees C and do a safety range for Silicon Photonics devices, which matching the device requirements. Thank you very much for your attention. Now it's time for questions.
Thank you, everyone. That was fantastic presentations. My thanks again to Lawrence, to Ashkan, and to Sebastian. We have a number of questions that have already come in, so I'm going to jump into these right away, and we'll get to as many as we possibly can. The queue is filled up quite well, so I don't think we'll probably get through everything, but we'll give it a go. Let's begin. Ashkan, I think this is one for you. What lessons can we learn from the standard CMOS industry to apply to photonics for commercial test and measurement solutions?
It's a very good question. Thank you, Mark. I think one of the things we have to understand as photonics engineers is knowing when to test something and calling it and saying that it's good enough. I think being researchers, we want to do an exhaustive test of every device on every reticle across the entire wafer and just say, okay, this is good to go. Practically, that's not possible, right? So I think one of the key lessons to be learned is to develop a proxy set of test suites to say, if this minimum amount of devices work according to spec, we can infer that the rest of them do. But of course, to practically do that, you have to build statistical data and build confidence, right? So we got to get our way there. But I think that should be the aspirational goal to get to in order to make this tractable.
Okay, solid, wonderful. Lawrence, I think this is good. Next one could be a question good for you, since it refers to the CPT-10, referring to the CTP10 detectors. Can you elaborate on the full range OPMs requiring only one scan?
Yeah, thanks, Mark. Yeah, absolutely. Yeah, the detectors inside the CTP10, they don't have the typical auto ranging going on on the background in the electrical side of the optical detector. So this auto ranging circuitry normally takes care about the amount of light or current, excuse me, that is created by the detector based on the amount of light that it receives. So this auto ranging can create glitches in your measurements results when this auto ranging circuitry changes state, so from one state to the other. And this we have seen in reality can certainly create glitches in dynamic ranges over 30 dB. So both the CTP10 and the CT440, they work differently. So in other words, we don't have that auto ranging going on. It gives you this clean one dynamic range from top till bottom. So with the CTP10 and CT440, you don't have to do multiple scans to come to results without glitches, and so it's very repeatable.
Okay, thank you, Lawrence. Next question up, and I think this one would be good for Sebastian. This presentation shows a surface coupling device. Is there also a solution for edge coupling device test available?
Yes, thank you. Yes, this shows a surface coupling device. As you have seen in the video and in the pictures, edge coupling is also possible with this setup. The positioners we are using here with the hexapods, or also the other alternative, are able to do also edge coupling devices. In this case, we need a different fiber holder to hold it in a different angle to do either test on single die edge coupling or to test edge coupling devices in wafer format when we test or bring the fiber into a trench close to the device. So yes, there are solutions available also for edge coupling devices.
Okay, wonderful. Thank you. Another question, I think this would be good for Ashkan. What are some obvious ways we got it wrong in the past, and how do today's solutions circumvent or improve on how we used to do things?
So I think moving into this world, one of the things that we should not do in the past is to think about the layout, fabrication, and testing as three independent entities. One of the things that we've spoken with Lawrence and Sebastian and others around this is just kind of the next step of where is this going, right? Maybe the webinar we can do in 6 months or a year from now to talk about it, ideally, would be to have the testing solution be informed of at the design time, so that when you're designing something, you're doing your floor planning, you're doing your layout, you keep your testing solution in mind, right? Because sometimes what we've done in the past, what I've realized the problems are artificial problems. Like if I knew how I was going to test it, well, maybe I would have designed it a little bit better. And believe me, that's a very expensive lesson, because you have to do 2 tape outs at least, or maybe 3 tape outs to learn some of those lessons, right? And then you just kind of get experienced and you just know. But in order to make this more approachable and more market adaptable, we have to come up with a solution that, abstracts those lessons away. So that's one key thing that I think we could do better that we've not done yet so far. But if the other two, Flora and Sebastian, you guys want to chime in on that answer, please feel free.
Anyone? Okay, well, I'll move on to the next question then, and if we want to come back to this, of course, gentlemen, please do. This next one I think would be good for Lawrence. Reference the passive optical component testers. Can anything be said about bringing the default wavelength accuracy, of plus or minus 5 picometer into the sub-picometer range?
Yeah, absolutely. So the Michelson interferometer inside the CT440 and CTP10, they guarantee plus minus 5 picometers at any given time, whether system scans or doesn't scan, which is more than adequate for most applications. There are, however, as I mentioned earlier in the webinar, there are certain PIC devices that need a higher wavelength accuracy. For instance, like ring resonators that are very wavelength sensitive. So for those kind of applications, Axfo offers two external acetylene gas cells, one in the O band and one in the SCL bands, that can be used as a reference while the system is scanning, bringing that wavelength accuracy into the sub-picometer range.
Okay, all right, thank you, Lawrence. Another question coming up, and I think this would be good for Sebastian. Is this test solution also available for manual probe stations?
Yes, I concentrated in this presentation on the automated testing. So going through an entire wafer, this was also the reason to have this project. So fully automated testing where we place the wafer manually on the probe station and then go through an entire wafer automatically. But it is certainly also possible to do this testing on manual probe station. So depending on the wafer size, also a manual probe station like 200 or 300 millimeter can be chosen. And then we just position the device manually. And stepping from one device to the other would be also manually. But for the optical alignment, we would still use the same type of positioners I explained in this presentation. And the reason is that with these positioners, we have a very precise and accurate alignment, and it's also very repeatable. So I can save a lot of time by using this kind of automated positioning also for manual systems.
Okay, excellent, excellent. Thank you, Sebastian. Another question coming up, and I think this would be good for Ashkan. How is the proposed TMM solution strategically different than what else is on the market today?
I think this brings together the best of all platforms, right? We have world-class testing equipment, we have world-class hardware like probing stages, etc. And we're fortunate enough to provide the wafer for now, but that can be anybody's, right? So I think what this is targeting is something that's used and usable by anybody at the assembly plant, the OSAT level, like I mentioned in my presentation, and at the foundry level, so that they can both look at this as a commercial solution and say, okay, this is apples to apples comparison. And as a systems company, as a product, and as the end product entity, I want to be able to ensure that what exists at the foundry exists at the OSAT, because if the foundry says, okay, it's cool, it's good to go, but then the OSAT tester is something different, then I have to worry about calibrating these two setups, and that's a pain. So by initially positioning the solution as something that is basically it's agnostic to who uses it and where it's used, we're able to come up with something that can be used either at the foundry, at the assembly, or at the customer, right? So I can put one on my production floor and says, okay, at the very end, I want to be able to test it too. And if all three of them are the same, they're using the same test platform, test solution, test software, test equipment, whatever, and they all three pass, then I can just say that, okay, these are all good. So I think that's one huge strategic advantage proposed here.
Thank you, Ashkan. Yeah, that multiple reliability across the markets and from the perspective of the various participants in the ecosystem is very key. That commonality, and I think that's been one of a problem we've seen with some earlier test and measurement solutions, is that one company might be testing it using one methodology, one set of equipment. Someone else along the value chain would test it a different way, and then they'd wonder why their results were so far apart. Next question, I think this is good for Lawrence. The integrated PIC test solution presented was around passive component testing, the CTP10 and MPI 3000. For active PIC device testing, can the OSA 20 be made part of an integrated test system?
Yeah, absolutely. So the OSA is equipped with 1 gig Ethernet ports, a GPIB bus, and 6 USB ports that can be used for remotely controlling the OSA in pretty much any environment. So Axfo can address any specific programming or integration requests based on what the customer wants. So we can do this either direct or with collaboration with MPI and HPE, or any third-party system integrator. We have done that too. Or Axfo can provide drivers and sample scripts to get you up and running.
Okay, Wonderful, wonderful. Thank you, Lawrence. Got another question, and this I think could go to Sebastian. This may be kind of an apples to oranges question, they say, but is it possible to say how much faster individual device testing will be using this new technology compared to some of the legacy techniques that you all are familiar with?
Oh, well, I mean, I have seen setups in labs, basically manual setups, where I mean, it can take you hours to set this up manually, to align a fiber in X, Y, Z. I mean, repeatability in Z is a very important thing, where we use a distance sensor here to always come back to the same height for surface coupling devices. So to set it up in previous system can take a very long time. So and now, as we showed here, it's done within seconds. And stepping to the next die is all very precise with the probe station, with this automated probe station and stepping. So testing a full wafer is much easier with such kind of automated solution than like very simple setup where you can maybe test a couple devices a day.
Yeah. I think we really have moved on, as one of the presentation slides denoted rather. We're definitely making that way up the evolution of our systems here. We're just about out of time, folks. I did want to take one last question. I think this is actually aimed right at Expo. So Lawrence, again, do the instruments support SCPI commands?
Yeah, absolutely. All of our instrumentation that was shown in this presentation here and more, of course, they all support the Skippy commands. Yes, absolutely.
Okay, excellent. Well, that was a quick answer, so we'll jump on to one others. I'll just throw this one out, but it may also be going back to you, Lawrence. Do you have any software that remotely communicates and control the testing? It kind of looks like they're trying to get at the idea of, could this be set up in a facility and then actually run maybe by another group that would be part of the team if they weren't physically present?
Yeah, there are a few different options here, of course, depending on the type of setup and the type of instrumentation involved. But the easiest way to address this is to use this turnkey solution as presented in this webinar here, and remotely control into the computer that is connected up to the system. So you would simply take over that computer from wherever you want to control that from and run the test. So yes, there are an endless scale of possibilities here, yes.
Okay, excellent. Well, thank you, Lawrence. Everyone, we have a lot of questions still left in the queue. I know we will never get through all of them today, so I guess it's both my regret that we can't spend more time here, but we know that everyone has schedules, and so I'm going to bring this to a close with our thanks from Angel Business Communications to our host today, Expo, Hewlett Packard Enterprise, and MPI Corporation. And of course, to our speakers, Ashkan, Lawrence, and Sebastian, who have given us such fantastic presentations today. Just again to recap for anyone who may have joined us late, the questions that we were not able to address today will be answered. In fact, I believe some of our experts have already been working on answers while other people have been addressing questions, so those will go out. Usually these are done as soon as our panel of experts can do it. We shoot for within 24 hours because obviously things do come up. But our thanks again to Expo, Hewlett Packard Enterprise, and MPI Corporation. Look forward to an email from Angel Business regarding the webinar and when the full replay is available for anyone who, say, missed part of today's presentation, or for those who registered earlier and were not able to attend live. So again, thank you today. Thank you for joining us. And thank you again to Expo, HPE, and MPI. Bye, everyone.